In aviation, even a small mistake in weight and balance can affect aircraft stability and safety. That's why understanding load distribution is critical.
To address this, we develop interactive weight and balance analysis for Cessna 208B system, the I-Wacs. Interactive weight and balance analysis for Cessna 208B system. When we talk about aircraft weight and balance, we're just not solving equations, but understanding how an aircraft responds.
But in most classrooms, this is explained using formulas and 2D diagrams, which makes it difficult to visualize in real life.
So instead of just computing, we created a system where students can actually see and experience the result. This makes learning more interactive and easier to understand.
The objective of the study is to develop I-Wacs, a 3D printed aircraft designed to enhance the learning and teaching of aircraft weight and balance.
Specifically, the study aimed to address the difficulty in visualizing weight and balance concepts by developing an instructional tool that integrates both physical and digital components.
The system was evaluated in terms of functionality, performance efficiency, and interaction capability, as well as reliability, safety, and software performance.
Finally, the system was assessed based on user acceptability, including instructional usefulness, learning engagement, and ease of use.
In this project, we focus on the Cessna Caravan 208B and the basics of weight and balance. It does not simulate full flight behavior but focuses on helping the students to understand the concepts better.
How to operate the system properly? Before operating the system, instructor supervision is required at all times. Ensure that the aircraft chocks are properly installed. Check the platform and make sure that there are no obstructions around the aircraft, sensors, and wirings.
Open the enclosure and inspect the system for dust, debris, and loose wirings or misaligned connection. Remove the aircraft's top cover to allow loading access. Get the storage vacuum miniature and place it in a safe place where it will not interfere with the simulation. After inspection, close and secure the enclosure.
Plug in and power on the system. Wait for the startup process to complete. Verify the sensors and monitor are functioning properly. Enter the authorization key to access the system.
Connect the hardware to the system interface.
Once everything is ready, the chocks can now be removed.
Perform calibration and verify that the system is ready for operation. These miniatures represent different loads such as passenger, baggage, and fuel. Each load must be placed in each proper section and to ensure accurate computation.
After logging in, the system automatically opens the lecture mode where we begin the demonstration. Miniatures are placed in the aircraft to simulate different loading conditions.
As the loads are placed, the system displays real-time values such as total weight and center of gravity.
To assess understanding, the system can switch to quiz mode. In this mode, the instructor set the load condition and correct values, which are hidden from the student.
The student enters the computed answers based on the given scenario. Only the required inputs are accessible, while the other controls are restricted. Once submitted, the system automatically shows the percentage of the answers and evaluates the answers as correct or incorrect.
For demonstration purposes, the system can also operate in exhibit mode. In this mode, the system automatically generates the different loading scenarios.
This allows users to observe how the aircraft responds without manual input. Disconnect the hardware from the system and confirm that it is properly disconnected.
After operation, exit the active mode and return to the main menu. Collect all the miniatures and return them to the storage box. Place the storage back in its proper location. Close and secure the enclosure.
Shut down the application and the computer system. Wait a few seconds before unplugging the system safely.
Reinstall the jacks. Finally, perform a last inspection of the platform, wirings, and surroundings.
The results of the study showed that I-Wacs effectively addressed the learning needs of the respondents and met the objectives of the project. The needs analysis obtained an overall average mean of 4.46, interpreted as strongly agree, showing that the respondents saw the need for an interactive instructional tool for the simulation and visualization of aircraft weight and balance concepts. The highest rated indicator with a mean of 4.65 showed that the respondents strongly agreed that a physical model or simulation would make learning aircraft weight and balance easier. This showed that the system addressed the difficulty in visualizing these concepts through a more interactive approach.
In terms of system quality, I-Wacs showed effective performance in functionality, performance efficiency, and interaction capability. The evaluation also showed that the system operated reliably and safely, while the software performance well in responsiveness, simulation accuracy, functional correctness, and interactive functionality. These results showed that the system met its objectives in prototype design and software performance. In terms of user acceptability, I-Wacs received very high ratings across all indicators, including instructional usefulness with 4.57, learning engagement with 4.50, ease of instructional integration with 4.47, willingness to use with 4.58, and overall acceptance with a composite mean of 4.54, all interpreted as strongly agree. Overall, these results show that the I-Wacs was effective, engaging, and highly acceptable as an instructional tool for teaching aircraft weight and balance concepts.
To further improve the system, several recommendations are proposed.
With I-Wacs, students don't just calculate. They understand it, see it, and experience it in real time.